the harmonic sine waves up close and personal. In particular, we're going to plot the harmonic sine waves of length 8 or period 8. And we're going to look at their real parts, their imaginary parts, and understand a little bit more about their frequencies and other properties. This is an experiment that I highly recommend you replicate on your own because you'll get a lot of intuition into how sine waves operate. All we're going to do is we're going to set up a time signal of length 8. So little n here goes from 0 to 7. And then we're going to look at the 8 harmonic sine waves that correspond to a period of this length 8. So k in this for loop is going to go from 0 to 1 to 2 all the way up to 7. And then given that value of k, we're going to form our harmonic frequency, 2 pi over n times k. And then we're going to evaluate that at all the time points n, and then we're going to plot the real and imaginary parts. Very, very simple to do this, and this will work just fine in your MATLAB in your edX browser. So let's execute the program. And now let's look at our sine waves. So the first thing we notice is on the left here, we're plotting the real parts of the complex sine waves, the cosine parts. And on the right side, we're plotting the imaginary components of the sine components. Each consists of 7 points in time. And then vertically, each plot, we're plotting a different k. K equals 0 all the way down through k equals 7. And now let's just interpret what is going on with these different sine waves for different values of k. So first of all, k equals 0, we can see very simply that k equals 0 in our sine wave formula basically means we're taking cosine of 0 for all n. And so our sine wave equals positive 1 all the time with a 0 imaginary part. So that's pretty simple. That's what happens when k equals 0. When k equals 1, plugging a 1 in here, we see we have the property that in this the period of length 8 that we're dealing with here in our sine waves, we see that our sine waves make exactly one oscillation cycle in that length of time points of period 8. Similarly, for k equals 2, we see that we have exactly 2 periods of oscillation expressed. Similarly, for 3, we see we have 3 periods of oscillation. And at k equals 4, which is quite interesting, and we'll look at this in more detail, we see we have the highest possible frequency of us because our signal is bouncing between +1 and -1. And you can't imagine flipping any quicker than that. K equals 4 is also interesting in this case because the imaginary part equals 0. And let's just understand a little bit more about this frequency k equals 4. Recall that omega in this case will be 2 pi over 8 times k equals 4, which equals pi. Okay? And recall that the frequency pi is the highest frequency that a sine wave can have, and that's exactly what we see halfway along this sequence of sine waves. So a very interesting point that we've seen up to here is that as we go from k equals 0 up to k equals 4, we see the oscillation frequency increases as we go down, increase k. From 0 oscillations to 1 to 2 to 3 to 4 oscillations in this one length of period 8. But then a very curious thing happens. We see that once we go from 4 to 5 to 6 to 7, we see the oscillation frequency actually decreases rather than increases. Here we have 3 oscillations, 2 oscillation, and 1 oscillation. And as a matter of fact, if we look in more depth, we can see that for the sine or the cosine components in blue, these signals are all identical to each other. These signals are identical, k equals 1 and k equals 7, right? Whereas these signals in the sine component are also almost identical to each other, except they're different by a factor of -1. Here we see the sine wave going up at the beginning of time, and here it is going down, but it's still a sine wave with one oscillation. So we might suspect that there's something going on here related to negative frequency, and that's precisely the case. And so let's study the case of k equals 1 and k equals 7, and let's just write out what these two different frequencies are. And in particular, for k equals 1, we can write that the frequency is 2 pi over 8 times 1, which equals pi over 4, right? And so we can think of this frequency as an angle, okay, an angle of basically pi over 4. Next, this frequency at the bottom, here we have k equals 7, and now the frequency is 2 pi over 8 times 7, right, which equals 7/4 pi. And we can ask what frequency that looks like. Well, that, or angle that looks like. Well, that is precisely this angle, 7/4 pi. Well, we can see that there's an alternative way to express this angle 7/4 pi, and that is as what? Negative pi over 4. And now we see that it's no wonder that these two signals look alike, identical in the cosine component, sine flipped in the sine component, because this first signal for k equals 1 corresponds to a frequency plus pi over 4, whereas for k equals 7, it corresponds to a frequency of minus pi over 4. So here we see the positive and negative frequencies playing a key role in these harmonic sine waves. So again, I highly recommend that you try this example at home using the embedded MATLAB in your browser, and you'll be much better for it when it comes time to study the discrete Fourier transform, or DFT, and FFT later on in week 3. In this second MATLAB experiment, we're going to continue the previous experiment into the harmonic sine waves of length 8. But here we're going to have a little bit of fun, and we're going to show how when we stack these sine waves as column vectors into a matrix, you get a matrix with a sort of some really beautiful properties. So we're going to visualize the harmonic sine waves as images in this example. So we're going to do the exact same thing that we did in the previous example. We're going to look at harmonic sine waves of length 8, and there are 8 of them. But now, rather than just generating the sine waves one by one and plotting them as time signals, we're going to actually generate them and stack them into a matrix D. We're going to stack them as columns into a matrix D, where the harmonic sine wave corresponding to a given k is the kth column of this matrix D. And here you'll note one of the tricky things that you're going to need to worry about in MATLAB, and that is that we're using n and k as varying from 0 to n minus 1, but in MATLAB that is not allowed. You have to start counting indices generally at 1 for building matrices and vectors, sort of a Fortran notation. And so you're always going to be having to add or subtract 1, which can get confusing and can lead to bugs in your code. Okay, so let's just execute this in our MATLAB window and look at what we see. So this is a plot now of two matrices, corresponding to a stack of the real parts of the complex sine waves, the cosine parts, and the imaginary parts, or the sine parts. And here, each column of this matrix is a sine wave of length 8, and this pixel of this image is colored in according to this color map, depending on whether it's a number between -1 that gets colored as blue, or +1, which is colored as red. And so this is very interesting to look at these matrices. First thing that we see about this, the real part matrix, is we see that the first column, or the first sine wave, for k equals 0 is in fact all the value 1, and we know that is the case. We can also see that the fourth column, k equals 4, oscillates between +1, -1, +1, -1, etc. And then we can see the other columns correspond to 1 oscillation, 2 oscillations, 3 oscillations per 8 samples. And we can also see that these columns are repeated due to the fact that we have positive frequency over here, negative frequency over here, and the cosine of positive or negative frequency signal is the same. Over here now, with the imaginary or sine components, we see that the imaginary part of the 0 frequency is 0. We also see that the imaginary part of the frequency pi equals 0. And then we see, just like over here, that we have basically 1 oscillation, 2 oscillation, 3 oscillations. But then we have a very interesting anti-symmetry, where again we see that these sine waves in these columns have the same structure, but notice that they're flipped. There's a sort of flip across the center point, and this basically corresponds to negative frequency. Basically, this is a frequency with, you can think of it like time running in a forward direction, and this is the same frequency, but time running in the reverse direction. Reversing the time axis or reversing the frequency axis results in the same sine wave. So this is just a fun example at this point, showing you how you can visualize signals as vectors. But what we're going to see later on in week 3 is that this matrix has a very special name, and it's called the DFT, or the discrete Fourier transform matrix. And it's going to be a very important transformation when we multiply this matrix by signals to create another signal. And basically what's going to happen is multiplying a length 8 signal by this matrix, with this real part and this imaginary part, is going to take us from the time domain, and it's going to map us into the frequency domain, which is a very powerful idea that we're going to exploit for designing different kinds of signal processing systems. The last thing that you should just notice is that these matrices have some very interesting symmetry properties, namely that the real part is basically a symmetric matrix, where if we draw a line down the diagonal, we see that entries on opposite sides of the diagonal take the same value, and that means it is a symmetrical matrix. Okay, whereas if we look at the imaginary part matrix, we see that it also has this real symmetry to it. Okay, and so these matrices are symmetrical, which is going to play a really nice role in the DFT, thinking about the forward DFT and the inverse DFT. But we'll talk more about that in week 3.